Okay, we are on to Chapter 5, Electrons in the Atom. This chapter has a lot to do with some of Newton's work with waves. It's going to seem a lot like physics, and it sort of is physics. But we have to understand what Newton has done with his work with waves to fully understand how an electron acts, where it's at, everything about it in the atom. So, the knowledge we have about electrons come from Isaac Newton's work about light. So the understanding the properties of light is important. Light is made of waves. Light consists of waves. There are 4 big main characteristics to waves. There's the amplitude to the wavelength, the frequency of the wave, and the speed of the wave. And understanding this has let scientists understand again things about the electron. Well, let's talk about these 4 characteristics of waves. Amplitude is the height of the wave from crest to peak, and you can see in the diagram there that the green arrows between, that's an amplitude. So the crest is kind of the, I'd say sort of the starting point, peak to the top and then back down. So that's the amplitude. Wavelength has a symbol there, it's the lambda symbol. It's distance between peaks measured in nanometers or nms. When I write wavelength, it looks like an upside down V. Frequency is, its symbol is V. It's the number of wave peaks that occur in a unit of time. It's measured in hertz. And you're going to have to remember that hertz is 1 peak per second. So hertz is equal to 1 over s, or 1 over a second. You're going to have to remember that when we start doing some of these mathematical problems. The product of frequency and wavelength always equals a constant, and that constant is the speed of light. And the symbol for the speed of light is a capital C, which is why when we're doing calories, you cannot just use capital C. Capital C is the speed of light. When we are writing out calories, big calories versus little calories, it's capital CAL or small cal. So the speed of light moves at a constant of 3.00 times 10 to the 8th meters per second. So we have this formula, the speed of light is equal to the wavelength times its frequency. And again, wavelength is the distance between peaks, and frequency is the number of wave peaks that occur in time. So the speed of light is equal to the wavelength times the frequency. So that C, or the speed of light, is a constant. That number never ever changes. So if the frequency gets larger, then the wavelength is going to have to get smaller. If the wavelength gets larger, the frequency is going to have to get smaller, and vice versa, because those two numbers multiplied together equal a number that never ever changes. So if one gets larger, the other one has to get smaller, and vice versa. And then after learning more about waves, they had this wave model, which said that light consists of electromagnetic waves, light consists of electromagnetic radiation, and that light consists of electromagnetic spectrum. And that spectrum contains the visible light, which of course is what we see, but a lot of the electromagnetic spectrum we can't see it. These would be things like gamma rays, X-rays, infrared rays, microwaves, TV waves, and radio waves. Then there was this scientist, his last name's Planck. He was able to predict the spectrum of radiation emitted by an object changes with its temperature, or predict the range of heat or energy emitted by an object changes with its temperature. And that kind of makes sense, and we can see that change by the flame actually turning red to blue to white. So we can see the change in temperature. The flame actually changes color. So the spectrum, that's the range of radiation, it's a different color. The range of color where heat emitted by an object changes with the temperature. So what that's saying is if we have a flame, the color of the flame will change depending on how hot or cold the flame is. And I can kind of show you that with the Bunsen burners if you remind me. You're going to have to remind me because I will forget that. And so with Planck's theory came this formula, E equals hv. E means energy. H is just a constant number. That number never ever changes, and it can be written in two ways. 6.6262 times 10 to the negative 34 joule seconds, or 6.6262 times negative 34 joules per hertz. Okay, as you can see, there is a typo there, which I'm going to have to correct. And then scientists learn that there's a restriction on how much energy objects can absorb or emit. They can't just keep absorbing and absorbing or giving off and giving off. And the restriction on how many, the restriction is, the reason it's there is because the electrons are at certain levels and they can only move so far. They can't keep moving and moving and moving and moving. When electrons move to different levels, depending if they're going up or down, heat is either absorbed or heat is given off. And these electrons can't move as much as they want. They're restricted on how far they can move within their shell. So the restriction, the reason that how much energy an object can give off or take in, it's all about the electrons and how far the electrons are moving. The word quantum is the amount of energy an object absorbs or emits. So when we're talking about energy objects take in or give off, we're talking about the quantum. It's quantum. So again, there's a restriction on how much energy something can take in or give off, and that restriction is due to those electrons. Those electrons can only move so many levels. Depending on if they're going up a shell or down a shell would determine if they're giving off or taking in electrons. And again, it depends on what they're reacting with also. So from Planck's constant, E equals hv, and from the speed of light, c is equal to lambda, or wavelength, times the v, which is frequency, there are some wave problems. And here are two wave problems. We'll do some more practicing of this in class. But I wanted to go ahead and do these two problems with you now. As always, you should write down the formula that you're going to use, and then you put the numbers where they belong, and then you solve. So for the first one, I am going to see what is the energy. So I see the word energy, so I'm going to have to use the energy formula. Okay, and I'm finding what is the energy, so I'm finding E. H is a constant. And there was two different labels for that, but I'm going to use the joules per hertz because I have a frequency in hertz. And if I look, this is like hertz over 1. That cancels with that, so I'm left with joules, and joules is a form of energy. And if I punched my numbers in the calculator correct, let me know if that's not right. My calculator was doing weird things earlier. So if that is not right, I'm going to have to re-record this or go back. Okay, so the second one is a certain light has a frequency of 8.72 times 10 to the 14th hertz. What is its wavelength? Well, there's only one formula with wavelength. Okay, and C is my constant. And if you wanted to, those constants, the speed of light and the h, put it on your periodic table so you have them. Okay, What is the wavelength? Well, here's the symbol for wavelength. I was given frequency. Okay, so I need to do some dividing here, because I need to get this sitting by itself. So if I divide this side by I have to divide this side by that same number. And then I'm left with the wavelength. Now, one thing when you're doing this, you have to remember. So what we have here really is meters per second, if you look, divided by hertz. Okay, which is meters per second. And remember, the other way to write hertz is 1/2. And then, so we're taking a fraction divided by a fraction, which is this. So by having meters per second over hertz, we actually have this right here. Seconds cancel, we're left with meters. And so this cancels out. We do our math here. And again, if my calculator was working right, and then what is its wavelength? Wavelength meters, that makes sense. It's length meters, 3.44 times 10 to the 21st meters. Like I said, we will have more practice on this, manipulating these formulas. But as always, put the formulas on your periodic table and put those constants there so you have them. They're always there in front of you.